Okay, so I guess I'll just say a couple of reminders. Um, there's a reading that is due Thursday. I've also enhanced some of the drop policies a little bit. So a couple of things that used to be drop one are now I think drop two. Like I think all of the three different categories of reading are drop three. With the schedule this spring, there was a lot more adjacency to holidays, and so I wanted to give people a little bit more flexibility. So there's that, and I think finally after this afternoon, I've figured out all of the bugs in any of the scheduling. So the to-do list and the Canvas calendar should be all up to date and ready to go. Thanks for those of you who've already sort of started working on the perusal and submitting the reading assessments. Perusal conversations have been great. Appreciated your engagement there. So for those who haven't taken a look at that yet, the chapter one reading that we'll be going over on Thursday, you can read it through perusal and get credit for that reading. And then there's a reading exercise you can do alongside that to kind of see the points that I've kind of highlighted, and then a reading assessment to kind of test comprehension before class. So all those are up and available. So any questions about the assignments or deliverables going forward? Yeah.
Almost more like valuable to do it on like the way you have it set up, so that you can like see, what you see is like the biggest focus.
You mean like is it more valuable to use perusal and to read it through there, or is that what you mean? Well, I mean, so you get credit for perusal, so I'm expecting everybody to engage with perusal. So so that would be so yeah, I mean, it's basically, if you've never used perusal before, it's basically just a PDF that there's already notes that have been highlighted for me that I've sort of said like, oh, here's an important part, or here's an expansion, or here's something maybe I don't agree with, whatever. And then it gives you the opportunity to add your own. Like, I didn't really understand what they meant here. Could you expand on this? Or I really liked this point, or I really disagree with this point, and so on and so forth. So it's basically just an annotated PDF. So yeah. Well, so perusal uses it uses a kind of machine learning method to assign a score of either, I think, 0, 1, or 2, I think is the score. Maybe it's 1, 2, or 3. And you can look at the perusal gradebook to see what score it's given you. And so there isn't like a hard number because there's a degeneracy. So it's like someone who revisits the documents a bunch of times gets more credit for that. Someone who comments more gets more credit for that. Someone who answers comments more. So there's a bunch of different ways to get the same credit. So if you look at the perusal gradebook, and the reason I said look that and not the Canvas gradebook is that they sync, but sometimes it takes hours for the perusal gradebook to sync to Canvas. So you might go into Canvas and you're like, it's graded out of 3, I think, and I only got a 1 on Canvas, but I did a bunch of work. Well, if you look at the perusal gradebook and you actually have the full 3 out of 3, it might take like 8 hours. I don't know why it takes so long to sync, but eventually that'll get synced through. Any other questions? Don't, put too much worry into it. It's just a way to me to provide a little bit more intrinsic motivation to go through the reading. Because I think the Moorcroft is I think that it's a nice book in that it's actually written for a business community, but most of the examples are sustainability. So it provides a way to sort of think about translating ideas outside of sustainability by kind of seeing the way that business strategists would think, but they're using the same dynamical systems tool that we learned how to use in this class. So the big reason why I kind of use Moorcroft's book is it kind of brings a bunch of things together. So just encouraging you to actually kind of take a look at it. But there's not ever going to be something like on a midterm that will be out of the Moorcroft book that I didn't say in lecture. So everything that we talk about in class, that's kind of the key things. And the book is supposed to complement what we do in class. And like I said, we'll have a whole lecture on Thursday about the chapter, reflecting on it, addressing shortcomings and so on and so forth. Okay, so any questions online? So those of you online, if you'd like to raise a question in the chat, the Zoom chat, that would be great. Or if you need to unmute and get my attention, that's also fine. But I'll periodically go back to Zoom and check for that. Okay, so last time we kind of ended with this, what is a model? Does anybody remember the kind of generic definition I gave for what a model was? models answer this type of question? 2 words. Yeah. What if? That's right. That's the generic definition. So anything that has model in the name will fit under the umbrella of it answers a what if question. And so it said like fashion models, for example, in principle, a fashion model answers the question, what if I would put on this jacket? Now, the answer to that question may be the wrong answer. It may be that the jacket looks good on him, but on kind of, somebody with my pudgy frame, that it just wouldn't fit, it wouldn't work that well. And in that case, if we were designing clothing for my demographic and we wanted to be honest about how things looked for my demographic, then we would iterate and we would go back and say, what's missing in this particular model? We have a dust storm, I guess. So what's missing in this particular model? And then we would go back and to test the hypothesis of whether that was missing. We'd go back and try to add that to this model and see if it answered the question any better. So effectively, you start getting things where the thing that's inside the model starts looking more like the natural system. But it does an okay job, even as flawed as the underlying fashion model is, at being better than like a hanger or just a table. So the models are not supposed to be perfect. They're not supposed to address every single detail, but they are supposed to at least give us a shot at answering that what if question. And there's a bunch of different examples of that. I mentioned a mouse model or a laboratory animal model helps answer that what if question for, let's say a pharmaceutical or something like that. This is a stand-in for human physiology. It's not a perfect stand-in. The answers won't always be correct, but it does a lot better than if we didn't have one, and it's very tractable. And then we can also talk about that with physics, mathematical models, physics models, like Bohr models of the atom. The Bohr model of an atom does a pretty darn good job until you start getting to certain quantum mechanical peculiarities. And then, they created an elliptical model, the Bohr-Sommerfeld model, which was a little bit better, but then it was worse in some other areas. Then it got atomic orbital theory, which was a totally different way of thinking about the electron, and so on and so forth. So these models change, and aspects that we thought were fundamental to models might disappear in later models that perform better. And so in 212, we are introducing system of dynamics models, which are a type of computer simulation model, which we're going to start defining what that means. But in short, we try to grab the salient features of systems we're interested in studying. And instead of studying them in the real world, we build smaller scale models that are still complex enough that were difficult for us to reason about mentally, simulate them on a computer that can unroll them in ways that our heads can't do, so many more sort of time steps, and then look at the outputs as if they were an experiment in the real world, and then make inferences on those before we actually go to the real world to try an intervention. We might find that our expectations in the simulation model don't match up, which tells us that our fundamental hypothesis probably is flawed. And so we need to go back to the drawing board on a hypothesis. And so it allows us to test hypotheses early so that we don't have to waste the resources testing them in the real world until we're absolutely ready. Very similar to like a mouse model. All right, so I sort of explained how this mouse model is a model system. What about this model? So I've got a woman that is hooked up to some respirometry equipment on a treadmill. You can see the output of the equipment here. And so this is a human, not a mouse. So would we call this a model system, and why, or why not? Any thoughts? Is this a model system? Yeah, why would you say that?
The ability to travel and make adjustments to the treadmill, to whatever you want, or to create or simulate through and picking up.
Excellent observations. And so just to sort of summarize there, it's a very tractable system. The treadmill allows the woman to move at various different speeds, maybe different angles of inclination. They can monitor all these different things, all in the comforts of the laboratory or the doctor's office or whatever. I guess I would then ask, what do you think the target system is if this is the model for it? So the,
could be a sporting kind of analysis for adjusting or monitoring inputs to performance.
But I guess I would say to that is like that. So we could say, say sports or performance or whatever. That could be, she could be the athlete, and we could be studying just her performance. So how do we tune her workout, routine, for example, to maximize its output? Or she could be a model for all white women, or she could be a model for all humans. Or, so there, depending on the research question, we might actually use the exact same experimental setup, the exact same model, but our scope of inference might be different. And so the results we get, their answers to these what if questions, so for example, she could have gone to the doctor's office because she wakes up every morning, has a hard time getting up out of bed, maybe at certain times of the day has really low energy, and they want to test her for one of these cardiovascular regulatory sort of things like POTS or whatever. And so they might put her through some sort of setup like this or a tilt test or whatever. But the thing is, like, even though she is the system we're trying to understand, walking on a treadmill is not the context on which we're asking the question about. So we're saying, why is she losing energy in the middle of the day? Well, she's not losing energy in the middle of the day because she's on a treadmill, but we can use a treadmill to ask questions about that, to ask what if questions about what would happen if she went through different exertion modes that we think we can simulate with this setup here. So even when she is the target of study, the context is so artificial that we would still refer to her as a model for herself in more general context. So again, it's a tool for answering a what if question, the what if being sort of, what if you were to be physically exerted, with this particular heart rate and so on and so forth. And this allows us to get into those modes and then see what the outputs would be, because we might not be able to instrument her in the middle of the day. Even if we could instrument her in the middle of the day, how she, on any particular day we instrument her, that may not be a typical day. And so, or that may be a typical day, and we're only interested in those atypical days. And so, so at no point, even when you're experimenting with a real system, you're probably, still capable of calling it a model. What I'm getting at here. So it's you're always expanding farther than the experimental setup. In this case here, is this a model system? This is a picture of an intersection in another country, dense traffic coming into this intersection, no stoplights. And we can ask, is this a model system? And for me, it is a model system because if someone, before I saw this picture, before I thought about this particular context, and this is a real picture, if someone were to ask me, if you went into a dense urban area and you got rid of all the stoplights, what would happen? And I would probably say, traffic would stop, there would be collisions, cats and dogs raining from the sky, there'd be death and destruction, and it would be awful, right? In fact, I think of examples even in Phoenix where there's maybe an accident on the 10 that closes it unexpectedly for certain numbers of hours, and the surface streets just become packed, and it takes hours to get anywhere and all that. And it's kind of a similar sort of thing that I, based on my experience, I would expect that this would not be a feasible way to run a city. And yet, although this is not pretty, when I look at this, I'm sort of surprised to see the kind of emergence of a traffic circle. And there are people that manage to be crossing the street without harm. Traffic is backed up. Again, it's not very efficient, but it kind of looks like it's everyday behavior. Like, it doesn't look like this is a special case. It looks like this is just how traffic gets pulled through this intersection. So it makes me say, there are some contexts where maybe we don't need stoplights. So, so this the what if question of what if we didn't have stoplights? Well, why this works here probably has to do with culture, other aspects of infrastructure, et cetera, et cetera. But the possibility of this amount of traffic actually being able to crawl through this intersection in a somewhat ordered way is something that I had never thought of before until I saw this picture. So it's like a dolphin pod or something that's sort of emerging out of this. And so that's an example where this can be a model system. It may not be generalizable. My father was an attorney. When he was in law school, they would actually talk about experiments that they set up close to the southern border in the middle of the desert, one side of Mexico, one side of the United States, traffic light in the middle of the desert, in the middle of nowhere. And then they would have people in the experiment hidden watching and seeing how many people actually stop at the red light and wait for it to turn green. And for whatever reasons, cultural reasons, on the US side, people generally waited for green, but on the Mexican side, there's no one else around, no danger to anyone. Then people would stop, they treat it like a stop sign. And so, it just goes to show that like there's a lot of baggage that goes into understanding how these complex systems work. But something that works on one side of the border may not work on the other side of the border, but at least it can give us a starting point for thinking things through. And that's kind of what this is doing here. So I would say this is a model system. And then things like the Titanic. I mean, this is, it sucked for everybody on the Titanic, but afterwards, the decades afterwards, we have learned so much about metallurgy, about building giant vessels in cold waters. Turns out that it's not just that they hit an iceberg, but it turns out that the particular metals that they made the hull out of, they didn't realize that when put in cold waters becomes as brittle as is like peanut brittle. And so under normal water conditions, if you hit something that was of the same hardness as this iceberg, it probably wouldn't have resulted in this situation here. So it's a far more complex thing that people learned about after this incident. And so it goes to show that when we build things and deploy them into the real world, we are experimenting with people who are unwitting participants in our experiments, not providing any sort of informed consent. If I have a federally funded laboratory, if I have a study where I'm getting money from the government and I am to put humans in my study, I have to go through this process called IRB, where I have to guarantee that the humans that are in the study know a little bit about the study and provide consent for being a part of that study. But if you have private funding, like Facebook, for example, then they don't have to do that. They don't have to give informed consent. They can put people in experiments without anybody knowing. So that's why, if people go to Facebook, then some people are going to see some sets of ads, other people other sets of ads, and they're going to run stats on that. And that's an example of people on Facebook, their own customers, becoming models for understanding their advertising strategies. And that's very explicit experiments, but even when we deploy technologies like this, we are doing experiments because if something interesting will happen, you can guarantee it's going to go on the books and we're going to learn about it. And again, it's going to suck for these people, but we're going to learn a whole lot more about it afterwards. And so when we think about these model systems, we'd like to avoid turning people into lab rats or lab mice in this particular case. And that's one of the reasons why we build these artificial models. Now, I wanted to give one more, I almost forgot about this one more example of unleashing an experiment into the real world. So analog braking systems are now very common. Pretty much every single vehicle's got them, even older vehicles on the road. But once upon a time, when you learned how to drive, you didn't have anti-lock braking systems, and so you had to learn to pump the brakes. And so if you just slammed on your brakes, you could get into a sliding condition where you would lose control of your car because the wheels would sort of lose their typical relationship with the road, and you controlled what the wheels were doing, but the wheels were not sort of connected to the road, then it didn't matter how you're controlling the wheels. And so they invented anti-lock braking and that was modeled after like a strategy that tended to work with humans is they'd say if you needed to slam on the brakes hard, slam, but they let off a little bit, and you have to manually kind of pump your brakes, and that kept your wheels in contact with the ground, and that kept you from sliding. And they said, we can automate this. And that's what anti-lock braking systems are, where they actually put a pump into the brakes here. And when you slammed on the brakes, there it would detect that you were in one of these conditions, and you would hear, and you can hear this in modern cars, kind of a whine, this like, and that was the brakes pumping at very high frequency. Now, when this first came out, there were a lot of skeptics. They would say, there's no way an automated system can pump the brakes better than I can. I am an awesome driver. And it turns out that when they released these things, ABS cars got into more accidents. And so that at first validated people's assumptions that these systems must be flawed. But when they actually looked at the data, so again, the fear here, it's going to increase front-end collision because the ABS systems aren't going to brake as well. But when they actually looked at crash data, it turns out that these ABS cars were getting rear-ended. And they're getting rear-ended because there's only 10% of them on the road. So 90% of the cars had huge stopping distances. And these cars could stop so quickly that they were actually put themselves in risk because they then became an obstacle for the sliding car behind them. And so, you didn't actually get a safety benefit with ABS systems until you had enough penetration that everybody had ABS, because there were so many people out there manually pumping their brakes that they ended up becoming a major liability for those who could stop quickly. So it almost was a safety benefit that everybody slid so far because they got out of the way of the person sliding so far behind them. And so that was an example where it shows this kind of iterative process of model building where they assumed that the ABS were not going to do as well as the humans. The crash data showed that actually ABS were doing better than the humans. And this real world experiment told us we had to update our mental models. And so now when people are thinking about autonomous vehicles and things like that, then this lesson here is that many of the features that we hope to get out of these technologies, especially the ones that involve humans interacting with those technologies, may not immediately realize their benefits until enough people are doing them or having them. And so that was really sort of, it changed people's minds about sort of things. So it just shows that, we start with a mental model, we might implement in the real world, we might learn something from the real world through all of these crashes and so on. So we would like to not have to hurt people. Like this cyclical process of model building would be great if we could do it without ever having to actually put people in collisions. And so that's kind of what we're going to get through in the sort of this class is how do we build models that give us the same insights or similar insights as real world experiments without ever actually having to pay the tremendous costs of implementing in the real world until we have a little bit more confidence that when we put it in the real world, that we aren't going to be super surprised by the outcome like they were with ABS. All right, so going into like other things, what can we use as models? So I just want to give you like models really can be anything. Again, that answers this what if question. Pictures can be models. So they refer to this as a beaver tail cloud formation. They refer to this as a wall cloud. And so you may not know, like, you listen to the name beaver tail, maybe, I'll get into this in a second, maybe that name's good enough, but you look at the picture and it kind of sits in your mind and you think, oh, okay, I can tell from that picture that that a bunch of other things look just like it. So if I need to answer the what if question of what if there was about to be a tornado, well, I have a mental model of something that could occur. If I see something that looks anything like that, then I know that there could be a tornado coming. So that's one thing. But the interesting thing is the downside of a picture is it's somewhat hyper specialized to a particular situation. There are the same phenomena might end up sometimes looking very different. These here don't look at all like this picture here, even though that they too are precursors of a tornado. And so in that particular case, sometimes it's actually better to not necessarily think in terms of pictures, but to come up with a lower dimensional representation or words. So if I were to say funnel cloud, instead of showing you a picture, then that actually kind of describes these as well as the others. And if I think about funnel cloud, I know what a generic funnel is. I know what a generic cloud is. I already have a mental model of those two things. And so that actually allows my brain to think, well, yeah, I can see how that is a funnel cloud, but I also can think about how these also look like funnel clouds. And so this is kind of an example of how we are always tempted when we build models to make them more and more tailored, detailed, fine-tuned, bespoke to a particular system that's out there. And sometimes when we really need to operate in a particular area where its peculiarities are important, then we definitely need those high definition models. There are computer-based models now called digital twins that are all based on this idea where you build as high fidelity of model as possible and you constantly keep recalibrating it with data because you really want that to be a picture of your system. But sometimes we need more generalizable insights. And the way you get generalizable insights, fundamental insights about systems, is often by stripping away those details that are the special cases and asking what's in common among all of these cloud patterns here. And the thing that's in common here is not that particular structure that we see in the picture, but is that it's a cloud that kind of has this sort of tail coming off the bottom of it that we can just abstractly call a funnel. And thus funnel cloud is somehow more descriptive than a picture of a particular funnel cloud. So that's a weird thing, is that sometimes losing detail actually makes models better. It comes at costs, but you do get benefits out of it. And that's something we'll talk about. Yeah.
That's kind of a very generalized statement. I mean, that's considering that all elements of the model are in fact of equal value. But if you look at things like business intelligence, there is a very strong concept of what's called a key performance indicator. So in reality, it's not that you want to just screw on things to make it simplified. You actually want to make sure that what you leave in there is in fact a key indicator.
Right. Well, that's true. And so, and that's what we're going to get to here. And it's not, and that's the point that I'm getting at. And thanks for sort of looking ahead to this, is not the size of the model, but or the correctness of the model, but it's that the salient features have been left in, and the features that sort of are complicating factors that don't really affect the answer have been taken out. And so if you leave the wrong things in, you have a bad model. If you leave too many things in, that can also be a bad model. The science of model building comes down to figuring out what the right things are. And that may vary from question to question to question. All right, so, but we'll get to that. So thank you for that comment, that was excellent. So other things that can be models, graphs can be models. So I can show you like from a statistical point of view, if I've got a point cloud here, I can represent that point cloud where I've got sort of high school GPA versus university GPA. I can say, well, I'll do a linear regression and I'll fit a line through that. And that line represents a prediction that captures much, not all, of the variance in this relationship. I'm not saying why this relationship exists or how it exists, but I am saying that there tends to be a correlation between high school GPA and university GPA, at least up to, say, 60% of the variance or so. And so if I know on average what the average student's high school GPA is, I can figure maybe what the average university GPA is for all students with that average high school GPA. So that's something that I can communicate in a graph, in a picture. I also don't need necessarily data for that. There's this oxygen consumption chart over here where it's communicating in a graph that an idea. It's not necessarily a true idea. I mean, in this case, this is a pretty well-tested one, but in order for you to communicate this idea about physiology, I can draw a graph. And this graph says that my hypothesis is that, based on my hypothesis about human physiology, I would predict that as you increase exercise intensity, you will increase oxygen consumption up to a particular point, that at that point, which I'm going to call VO2 max, after that point, you'll be able to continue increasing exercise intensity, but the way oxygen is consumed in the body will change, and no more oxygen will be consumed, even though intensity will increase. So the body will start getting its energy in different ways. And so that represents an idea about human physiology communicated as a graph. And this graph is communicating a prediction. It is a model, you know. And what I like about this cute little cartoon here is they put these red dots on here. These red dots aren't data, they're just dots on top of the line. But they communicate a what if of what if you did this experiment. And this is saying that if you did this experiment, we would expect the dots would be scattered around this line. You take the red dots away, it's communicating the same idea about the human physiology. We put the dots in, and it's actually really telling you that you could run this experiment in a environment like the woman on the treadmill, and you would get data that would fall along this line. So graphs can be models. I talked about this graph in an experiment or an example we had last lecture. So that's, you know, so models can take a lot of different shapes and sizes and forms. They can be physical, they can be mathematical, they can be computational, they can be mental. But the key thing that links them all together, the salient feature that defines a model, is it answers a what if question. So if I were to sort of say, you know, more broadly, we have hypotheses that we form. Those hypotheses lead to predictions, and the models help us get there from hypothesis to prediction. They answer a what if question. And the predictions that come out of that, if we compare them to what goes on in the real world, if those don't line up, then rather than saying our model's wrong, what it actually usually indicates is that as long as we've built the model correctly, our hypothesis needs to be updated and the new model built based on the updated hypothesis. So there's a lot of focus on whether models are right or wrong, or whatever. Models are never right. Models are an embodiment of a hypothesis. And if the model's predictions are wrong, it's not the model that's wrong, it's the hypothesis that needs work. And so that's what we'll talk about in sort of this course. All right, so with that, I hope you start thinking about other uses of, you know, just colloquial uses of the word model. Like, where does the term model citizen come from? So anybody have any thoughts about this? Like, why do we refer this thing, a person or an idea, as a model citizen? What does that mean, and how does it fit into this idea of a model? Yeah.
I feel like a model citizen would kind of answer the what if question of like the perfect citizen, or maybe like really my perfect citizen. Maybe someone that is kind of exceed expectations on the point that a model like would have be all work harder kind of.
I think that's a great answer. So that is one way to answer this question here, is that the idea here is if you know, everybody, you know, who knows how everybody behaves, but if you could point to an example, an exemplar, somebody who always behaves a particular way, or an idea of somebody written down, you know, on a stone tablet somewhere, something like that, and you could say that these are what we think the perfect or the best you know, citizen should do, then that model citizen would answer the what if question of, you know, what if I saw a red light? Well, the model citizen stops at a red light. Do you stop at a red light all the time? Well, there might be some cases when you don't, but ideally you stop at every red light, because that's what the model citizen would do. So that's one way to view model citizens, is it provides the answer to the what if questions. What would the perfect, whatever that means, and that's kind of suggests the next definition, citizen do under these circumstances? Any other thoughts about model citizen? So for me, when I think about model citizen, like I get to this, like, what do we mean by perfect citizen? How do we decide what that model citizen is? And for me, that makes me zoom out to think at the system level. And I think about, like, I have a model of society. And in that model of society, in that ideal model of society, everyone stops at stoplights. Everyone votes. Everyone, you know, does these certain, you know, things. And if all of those things happen, then in my hypothetical model of society, then I would get certain positive outcomes at a societal level, in theory. That's my theory of society. And so model citizen, you can say, where does the perfect come from? It might come from the model of society, a model society where we get certain outcomes under the assumptions that people behave in certain ways. And so it may be that not everyone's going to vote. Well, in our model society, where everyone votes, we get this particular outcome. Then we can start asking questions about, well, what happens if only 50% of the people vote? What happens if only 90% of the people stop at stoplights, and so on and so forth? So this idea of where does the normative, citizen come from? Where do the norms come from? It's my claim that they come from deeper ideas about functioning society. There might be ideas about functioning society in other cultures that involve, cannibalism and running red lights and things like that. And for that group, that leads to particular societal outcomes that they view as positive. And that may not be our culture, but they too would have a model citizen that would fit into that kind of model of society. So there's things to sort of think about. It's like, where do these terms come from, and how do we challenge them, and ultimately what do they mean, and what assumptions are we making when we say the model citizen, votes or something like that. So the big thing, regardless, of not only do models answer what if questions, the models all have the GIGO property, garbage in, garbage out. The idea here is that a model is only as useful as its assumptions are realistic. This is a little bit like that conversation about what to leave in models and what to leave out. So given this example of the fashion models here, the general idea of putting a jacket on a human to give me an idea of what that jacket might look like on me is a good idea. That's something I can get behind. But which human you decide to put the jacket on, that's where the garbage in, garbage out comes out to be. If that person is not a representative example of the target system, let's say me, then I'm not going to be able to make a good inference from the output there. And that's going to go the same for our computer models. We might find that we draw a model that captures what we think all the relationships are in, say, recycling systems or something like that. But then when push comes to shove, the computer asks us, what parameters do you want to set? What's the compliance rate for recycling in this community? And you arbitrarily say, I don't know, 100%, and then you run the model. And you get these beautiful outcomes where everything's green and trees start coming back and carbon dioxide gets scrubbed out of the air. And you think, my gosh, everything's going to be fine. And it's not your choice of relationships that was wrong. It was your choice of parameter, that recycling compliance rate. You set it to an unrealistic level. That was the incorrect fashion model you put underneath the jacket. So in reality, if you set that to like 50%, you might get a qualitatively different output from your model. So that's what I mean by garbage in, garbage out. You can have a good looking model on paper, but when you really drill down into the parameters that need to be set for the computer to actually do something with it, if those parameters are set to unrealistic values, the apparently good looking models is going to have results which are probably not going to match results if you were to implement that in the real world. So that's what I mean by the GIGO property. And that will become more clear as we start building models. But I just want to keep that in the back, in the back of your mind. And again, I like to bring up the fashion models because I think they're an excellent example of that. Is that trying on clothes is not a bad idea. Putting clothes on the wrong person is the bad idea. All right, any questions or comments about that? All right, so ultimately, and come back to a quote you've probably heard before. A lot of people misinterpret this quote before. Sometimes when I hold this pointer that direction, it doesn't quite work as well as I would like. All right, so so this all models are wrong, but some are useful. This is a quote from George Box, sort of a famous statistician. Now, a lot of people think of this as a criticism of modeling in general, but that's not what Box is saying. Box was a modeler. Box was a big modeler. He's a huge statistician, really influential in the field. What Box was saying is not that models are bad. He was saying, no. The practical question is how wrong do models have to be for them not to not be useful? So all models are wrong, but only some are useful. And those that are useful are the ones where you've chosen the right thing. So you've chosen the right way for the model to be wrong, in other words. So you never can get a model to match reality 100%. But you can get models that differ from reality in a bunch of different ways. And your job as a modeler, which is a hard job, is to choose the model that differs from reality in such a way that its outputs are still informative. And the difference from reality is going to make that model tractable. It's going to make it a simpler model that you can actually build on a computer and run. It'll finish in a day or in a minute or in an hour. It won't actually take like a month to run. It'll be something that allows you to actually make a prediction and then make some sense of it. So we have to make models simpler than the real world, because otherwise we just work with the real world. But we have to simplify them in the right way so that in the simplification process, we don't break the model and make it totally divorced from the real world. And that's something that we're going to also try to talk about throughout the semester. So any questions about this distinction? That, you know, this quote is not a criticism of modeling or math or computers or anything. This quote is an instruction for how to build models correctly. Yeah.
Well, isn't there some component that you have to think of that's different than elements? In other words, elements being something that is, you know, simple, you know, kind of like Einstein and his, you know, idea or theory should be rather simple, but not too simple.
Right.
You know,
Just simple enough.
That you can only, unless you want to have a better word than elegant, where you've got something that maximizes the value of the computation and minimizes the effort to get it.
Right, right. And later in the semester, we're going to refer to a term that we'll call boundary adequacy. And it's this idea that you can start, so as you start reading chapter 1, you're going to read about a very basic model of a fishery that leaves out a lot of stuff that could be in a fishery. Now you can gradually start, and so we can put a boundary around all the things that are included in that model. And now we can grow that to include other things in the model. The model gets more complex. And we grow it and we grow it and we grow it. And eventually you reach, like you say, sort of the sweet spot where the marginal returns from adding things into the model diminish to a point where the added cost of adding complexity is greater than the returns from adding the realism. And finding that sweet spot is finding the so-called boundary adequacy of these models. All right, any questions or other comments? Okay. All right, so, and I just checked the site that runs this link right now is requiring me to generate a new link as part of a marketing scheme that they added in between spring and fall. So, so this right now, if you tried this, doesn't work. But next class, now that I realize that that's the case, I'll fix this so that if you do want to submit anonymous questions, you can do that via the link that'll be on the slide or the QR code that's on the slide. But of course, you can raise your hand or you can raise a comment in the chat. All right, so I normally do an attendance exercise. I'll do one a little bit later. So, but just to keep going here on this momentum. So recognizing types of models. So we're focused on mental models here. So when you look at this image on the on your left, what do you see? What are some of the first things that come to mind? And those online, feel free to put things in the chat. Like, can you just look at it? What are some of the first triangles? That's one great thing. Any other comments? So triangles is one option. Anything else you see? Circles, triangles and circles. That's good. Yeah. Three angles and three circles missing a piece. Okay. Yeah. Pac-Man, that's another common one. This sort of shape of the famous video game character. I gave this example in a class once, and a woman said, I see three Pac-Man going into a room where there was a ghost that was hidden and they're all searching. Like, she had a whole story that went behind it. Any other comments? Any other things you can see? Some people say Star of David, six-pointed star. That kind of comes up too. But what's interesting, if you really then look at it, try to strip away everything your brain is doing, none of that's there, right? So there are no triangles that are drawn here. You could say there's maybe three angles for sure. There are no circles. You know, you might say, like, your brain might conjure up a idea of, well, what if there were three circles and a triangle, and there's a white triangle got placed on top, obscuring all the other ones, and maybe that would have created that. And online we've got, you know, circles as well. And that just goes to show that, like, your brain is constantly sort of raising causal questions, coming up with hypotheses, and then using what if questions to generate predictions to compare to the real world to test those hypotheses. And so when you say, I see, you know, triangles or whatever along those lines, what you're really saying is that there is a hypothetical world that my mind generated a picture of outcomes of an experiment. That's a mental model. And the outcomes that were predicted match these outcomes. And so we sometimes call, so there's a logical framework where we call this abducing or abduction, where we're coming up with hypotheses which may not be mutually exclusive. So there could actually be a set of them that all have the same possible outcome, where we're trying to come up with possible causes. Your brain is doing it all the time, and it does it by way of mental models that unroll those hypotheses in your brain. You know, similarly, I can look at this cartoon. What do people see when you look at this figure here on the right of the screen? And again, online, you can feel free to put it in the chat. First things that come to mind. Okay, I see Brazil 1985, which I am embarrassed that I don't understand the reference to. I will have to look that up.
It's a ridiculous sci-fi movie, and in it, they cut holes in the ceiling to like break into someone's house.
I just heard an explanation that it is a sci-fi movie where they cut holes to break into someone's house. So cutting holes, that I think is sort of probably related here. Anybody else see other things here? Kind of similar to circles, or I mean, what's going on? Or what pops into mind? Does anybody see a man? Right, so I think man is something that probably pops up a lot, but which is interesting, because like if you think about this figure here, there's nothing about what's drawn here matches human physiology or anatomy and physiology at all, right? So like I have a pretty big nose if I take this mask off, but I mean, but nowhere near this, in that like this really tiny head. You know, just in general, like if I were to cut this out and stand it up next to me, you would not confuse it for another person standing in front of the room, right? And yet I think we all can agree, we see a man. Cutting of holes. I think when I said cutting of holes from the online suggestion, thank you for that, I don't think anybody in the classroom said, well, I don't see that. Where is the cutting of the holes? You know, so that there, you know, you can see down here, there's this thing that's going on here, and your mind came up with a hypothesis, cutting of holes. It unrolled a mental model of what that would look like. It made a prediction, and lo and behold, maybe this is similar to what your mind's eye had in mind. What's the shape of the hole? I heard a circle. How many people would say circle? Say most people here. When we look at the drawing, though, there's nothing circular about it, right? This is way longer than it is tall. You'd say, but perspective. Again, mental model, right? So you could have chosen a slightly different perspective, and the hypothetical cause of what's going on here might have been cutting an oval hole. You know, a lot of times I get people responding to this, and I've had a surprising number of students comment on things about this person's personality, whether they deserve it or not. You know, but so there's some aspect of that your mind is filling in a lot of these gaps. And I bring this up, and we're going to do, you're going to see more of this in this first assignment that is coming up. Is that before we can start building quantitative models, we have to start learning to unroll and sort of peel the onion that is the mental models, figure out what our brain is doing to fill in those gaps. There's a lot of this valuable stuff that we need to make sure that we're putting down into our computational model, because the computer, it ain't got any of that already in it. So if there's some important insight up here that you've gained over your years of experience, you need to recognize it and put it down, because it's not going to happen on its own. You know, so the computer only does the few things you tell it to do. So that's why we really got to learn to become cognizant of what our brain is doing. Another example. So this is sort of famous painting hanging in the Louvre that, you know, this up top here shows two bicycles with a conjoined front wheel, the bottom, back wheels together. caption here, this is a model for fiancés. Caption here, this is a model for a couple at the instance of a divorce. And immediately I hear giggles, right? So I just see bicycles here, but we get it, right? So here, you know, you've got your whatever, your teenage love. You decide that you're going to marry this person. You're enthralled with this person. You just want to be closer and closer to this person, but you can't get any closer than you currently are. Like this is the, but all you want to do is get closer and closer, and that's kind of what is here. Something happens in the relationship down the line, and turns out you want nothing to do with this person, but now you're married and stuck with them. And so until you can get out of that, you want nothing more to be apart from this person, but your marriage, your kids, your home, whatever, are keeping you together. So none of that is depicted in these, but your lifelong experience, adds to this. And even if we cut out the relationship stuff, I can ask, like, do these models, would they actually work as bicycles, as tandem bicycles? Somebody's built these models. You can find actually these things that have been built in other art installations, but I don't actually have to build them to know if they work. Because I have mechanical models in my head, mental models in my head of how a bicycle works, and I can predict a bunch of different outcomes that would happen if two people tried to ride this bicycle, and none of them would be the normal outcome of a tandem bicycle kind of moving in the right direction, right? So I don't actually need to build it in the real world because my mental model is doing the heavy lifting for me. So, similarly, a fishing boat here. So this is an example where you have a mental model of how to steer this thing. And so the first time you've ever had maybe you've never had this experience, but maybe you have, you sit in there, the first time you're there, you're looking ahead, and they say, all right, we need to go left. And so your experience, or let's say the first time you're backing up a car when you're learning how to drive, and you want to move the tail end of that car left. And your general mental model for how to drive is that the interface you're given does what you tell it to do. So I might want to turn the steering wheel left, or I might want to push the rudder to the left in terms of where the handle is. And after you do it, what happens is, I thought I had an animation. What happens there is the boat is going to move the wrong direction. And very quickly, you're going to update your mental model, and you're going to say, oh, shoot, it's reversed. And it might take a little bit of practice, but eventually you'll get a separate model for when I drive a boat. I have to use reverse steering. When I drive a car forward, I use forward steering, and so on and so forth. So our mental models are making predictions of what would happen if we were to push on these things, and we make use of those to make our way in the world. Now, sometimes the mental models are not very good. So this is sort of a famous example that have done studies on these, and they survey people of different ages. And I'll read through it and then sort of talk about why this is an interesting example. Well, you might anticipate why. So a man and his son are driving in a car one day, and they get into a fatal accident. The man is killed instantly. The boy is knocked unconscious, but he's still alive. He's rushed to the hospital and needs immediate surgery. The doctor enters the emergency room, looks at the boy, and says, I can't operate on this boy. He is my son. Now, in this story, if you ask older audiences to make sense of this story, there is a large proportion of them that don't get it. They just cannot make sense of the outcome here. If I ask younger audiences about this, then there's no puzzle. And so I guess I'd say, like, what about in this crowd? So can somebody give me sort of a thought about this outcome here? What does this sort of tell you? Yeah. Doctor could be the mom, could be, what's another possible outcome? Okay. Other dad, right? So could be two dads, could be a dad and a mom. So if you have a mental model where you ask the question, what if there was a doctor? If your mental model says that doctor must be a male, then, and your mental model says, what if there was a relationship? If your mental model says that relationship has to be heterosexual, then this seems like a paradox. But if you grew up in a world where the experience that got layered on top of your mental model is different than that. You grew up in a world where doctors are 50-50 male or female, or maybe majority female. Or you grew up in a world where you're very familiar with plenty of homosexual relationships among men. Then in that case, you read this, and you don't see a problem. I've been showing this example for years in different modeling courses, and even in the past, I don't know, say 10 years or something like that, it's been interesting to me to see, like, initially I'd actually get very slow answers, but then I would, a lot of people would immediately sort of start answering, well, gotta be the mom, gotta be the mom, gotta be the mom. Then I hit a point where I would start getting, oh, gay dad, gay dad, gay dad. And then I'd say, what else could it be? And then crickets. And so it was just fascinating to me that, like, there was a rise in awareness of that, that women and men were in professional jobs were gaining parity, at least representational parity. And then once there was more of an awareness that gay men were, the relations with gay men became sort of more normalized in, I don't know, the public sort of, I don't know, the zeitgeist or something like that. For whatever reason, the idea that women would be in professional, it seemed, at least among the students that I've been teaching, seemed to kind of be decreased a bit. Now it's sort of back up where, I teach another class this semester that's similar to this class. I gave the same example today. And again, the first example was mom, and here's a mom. And then very quickly after that, gay dad. So it's just interesting to me. But the point here is that, all mental models are wrong, but some are useful. And you can ask yourself, how useful was your mental model of the world? And where does that mental model come from? And so that gives us kind of our definition of mental models. The strength of mental models is they're a tremendous store of information. So when we think about mental models, they have been developing and iterating and getting better or more complex for your entire life. And so we have to value them. We have to value the experience of people who are practitioners, who have gone through these things. Mental models are kind of important to that. But the weakness is, if you move from one culture to another, or if times change, or if you're trying to describe phenomena which changes over time, even in a short time window, it's hard for our brains to kind of keep up with that. And so mental models are really good at particular complex situations, especially if the situations are a bit static or tailored to a particular, like if you were to ask a real estate agent about New York versus LA or whatever, they'd be able to tell you, like, oh, well, in the LA market, you got to do this. In the New York market, you got to do this. Like, they know all of those sorts of details. And those details probably haven't changed very much because those cities always sort of sit in kind of a similar position. But if you ask them about, what would happen if you were to take a water balloon and throw it a particular way, that's something that, in theory, like computer models are really good at predicting that. Mental models are just crap at explaining, what the shape of that water balloon would be at any instant of time through its evolution. So that's kind of the weakness there, but we have to sort of say, there's a lot of strengths there. So what can we do to combat those weaknesses? And that's what the attempt is here for quantitative modeling, which is one of the things that we talk about. It's one of the main focus of this course. And so the idea here is they're supposed to be better at handling complexity and dynamic change, but they do leave a lot of stuff out. And so this will be our major challenge throughout the semester, figuring out what to leave out and what to leave in. And so that's the thing we're always up against. They take different forms. They can take mathematical forms, computational forms. We'll kind of define all of that. But that's the big contrast I want you to see between mental models and these quantitative models. All right, now there are multiple types of uses of quantitative modeling. So I'm going to kind of go through these three uses here. So the first one here is prediction. That's what we go through first. So this is kind of a very traditional form of quantitative modeling. Every time you ask what the weather is going to be like today, they query a quantitative modeling that makes a prediction. So it takes data in about where the clouds are right now, what the humidity is, all these measurements, puts into a model of the atmosphere, and then it makes predictions over a particular forecast zone. So the next hour, the next couple hours, the next couple of days, and it makes predictions about the weather. And so in this case, these are actually trying to make a real prediction about what is definitely going to happen in the next couple of days, maybe with the uncertainty. So here's a hurricane, we know where it is now, here's a cone of where it might be in the next couple of days. And so that uncertainty cone has to keep kind of being updated. So that's one way we can use quantitative modeling for prediction, figuring out what's going to happen. The next way we can use quantitative modeling is inference. And so in this case, this is trying to use quantitative models as a lens on which we can take data and try to look underneath it all and say what might be going on to generate those data. So we take data that it could be sample data from a real world, it could actually be sample data from a simulation, and we try to maybe test some hypothesis. So if this is the reason for, if this is what's going on in the fundamental process, then if we experiment in this particular way, we should get these outcomes. And once you get a bunch of outcomes from an experiment, you can then fit a model to it. And if that model doesn't match the predictions that you had in your hypothetical model, then so if the statistical model doesn't fit the prediction, the model from your sort of your hypothetical model, then that indicates that there might be something wrong with your hypothesis, and that might not be all that's what's going on underneath it all. So this is an idea of learning through experimentation, where we take data about the real world, we use that to test ideas about how the real world might be described, the processes that might be describing that, and then based on the mismatches there, we maybe get rid of some of those hypotheses, or we augment them with additional hypotheses to make them more complex. So that's what I mean about inference. So prediction is like what's really going to happen next. Inference is what's going on underneath it all right now. Then the third way that we use quantitative modeling is narrative, storytelling, trying to show me the numbers, as is popularly said here. So I give kind of this example from back when Obama was president, big downturn in the economy, there's this recovery plan. And so Obama could say, we're gonna have a recovery plan, it's gonna be great. And he'll say, show me the numbers. And so they say, well, what we did is we took our best economists are out there, took all of their experience, we put it in to a quantitative model, and that either had the recovery plan implemented or not implemented. And we generated two graphs from that. And so the with recovery plan is the dark one, the without is the light one, and we're plotting unemployment rate over here. And so what they're trying to show with this quantitative model is that with the recovery plan, the unemployment rate doesn't reach its high, and it comes back down quicker to its sort of baseline level. But without it, it gets a lot higher, and it stays higher for longer. So this is using prediction, but it's not really using it in the weather type of way. Like in the weather prediction way, it's like, do I need to bring an umbrella to school tomorrow? But this is more of telling a persuasive story. So this is not actually helping the decision making, but this is helping to communicate why the decision was made through the quantitative model. And so sometimes simulations can better capture a complicated idea than mathematics, for example, than putting a bunch of economists and just having them spout out hand-wavy explanations. And then, I give kind of examples here where explaining, for example, CO2 and temperature, but I put this one down here because I want to show that narrative can be misused. So if I were to take, I guess I'll back up here so we can see this. On this axis, this is years from 1900 to 2010, and this is CO2 levels on this axis. And then on the other axis, this is global temperature anomaly. And so the global temperature anomaly is in red, and in green and in blue are CO2 levels at two different locations, one in Antarctica and the other one in Hawaii. And what this is sort of showing here is that, that there is a relationship between CO2 levels and global temperature. So that's communicating an idea, it's telling a story there. But, if you were to zoom in on a small set of dates, you might be able to demonstrate an opposite relationship or no relationship. So that's an example of, again, how models can be manipulated. The idea of comparing CO2 and temperature sounds like a good one to a bunch of different people, but if you manipulate the ranges on which you explore that, then you can tell a totally different story. So that's garbage in, garbage out. is the same sort of example here. If you look at the whole data set, you get what looks to be more like a pretty compelling relationship between them. But if you focus on a narrow portion of it, then you might actually be able to tell a different story. So we have to be careful with narrative because it can be misused. Okay. All right, so questions about any of those three different methods there? The prediction's looking ahead, inference is sort of looking within, and the narrative is using models to better communicate a story or a hypothesis. Okay. All right. Now, quantitative modeling, we can break that further up into three different types of models. And they all kind of build up to this third one, which is the focus of this course. And so the first type, this is kind of Calc 1. And so you can build, so this model that I've got up here, this mathematical model, it's three coupled differential equations. So if you're not familiar with this notation, S with a dot over it is like saying ds dt. This is like saying ds dt, di dt, dr dt. So the rate of change of S, which in this case, this is a so-called SIR model, which you've probably heard about in ASU 101 or SOS 101 or other classes. This is a population model where we consider an average population with a certain number of susceptibles to a disease, infectious with the disease, and recovered from a disease. And we see how the numbers of those three different population compartments change over time. And so they're saying the rate of change over time, and I'm not going to quiz you on how to read this. We're going to effectively learn how to build this graphically, but I'm not expecting you to know how to read this. I'm just giving it as an example of an analytical model. The model you can write in math as three coupled differential equations. And you can, using methods from calculus, you can ask, okay, as time goes to infinity, what are the steady state values of the number of people in each one of these three boxes, susceptibles, infectious, and recovered? And with a little bit of math, you can actually solve for equations that tell you what those will be as kind of time goes to infinity, when this epidemic is over. And that's nice that you get a formula that relates parameters with numbers, and you can see how those parameters change and all that, and you can analyze the formulas that come out of that. That's a plus. The downside is this is not really readable, right? So you have to be a specialist to understand what the heck is going on here, right? So that's one thing. The other thing is it only tells me what happened at, say, the end of the epidemic. So in order to do the math, we often have to make additional assumptions, which allow us to cut out a huge portion of the system we actually care about. I might not care about how many people managed to survive without getting sick. I might care about, during the transient period, how many people were sick at any instant of time, because that might be most important for my hospital capacity and things like that. But solving for that mathematically is a lot more difficult. And so that's why we typically solve these types of coupled differential equations only kind of at steady state at the end when they're all over with. Now, in order to get the middle of it, what we can do is give up on getting a formula and do what we call numerical methods. And so, so in this particular case, you can take a population model. This is a different one, but it's the same sort of idea, where instead of asking, instead of saying, solve this and give me a formula out, what you can do is you can put a mathematical model down that describes how something changes over time. And instead of saying, how does it change broadly over time, you can say, what if I know what it is at time 0? What is it going to be at time 0.0001? And if it's really, really close together, I can probably replace that complicated calculus with a little bit of algebra. And then if I recalibrate at time 001 and do it all over again, then the approximation that I get will end up tracing out what I would have got if I would have done the math. And that's what we refer to as numerical methods. It allows us to fill in the gaps in dynamical systems, in systems that change over time, so that we can actually see an approximation of what they do in the middle there. So throughout the whole evolution of the system. But we lose the formulas. And so all we have is the graphs that come out of it. So in some ways, it's a better communication tool, but it's very approximate. So if somebody were to say, like, what's, if I were to change the, a quarantine level or something like that, how would this change? the only way I can evaluate that is by rerunning the model. Whereas if I had a formula, I could say, well, if you look at the formula, quarantine rate shows up here. So if you increase Q, then this other thing is going to increase in a particular way, and I don't have to rerun the model. So the formula gives me a lot of insight, but the formula describes a very narrow region of the future, whereas this tells me about all of the future. But if I want to make a change, I got to change it in this whole spreadsheet and rerun the spreadsheet. And if they say, well, what if you need to add another complicating factor? I might need to totally scrap this spreadsheet and rerun a whole new spreadsheet. So these numerical methods are good, but they're not really flexible enough for us to use for decision-making tools. So what we're going to do in this class are simulation methods. And simulation methods basically take numerical methods and they wrap on top of them a specialized software that allow us, instead of writing all those spreadsheets, we can draw diagrams like this. And we're going to learn how to read these diagrams, but this is that exact same SIR model that I just showed you, but it's in this graphical framework. And we're going to learn how to do this in this class. And then when I hit play on this model, it will, behind the scenes, draw up one of those spreadsheets, one of those numerical models, and do the sim for me. So then if I can change this diagram and hit play again, it will then create a new numerical model. So it gives me all the benefits of the numerical model, but it allows me to very quickly and very flexibly change the system so that I can experiment with it and make it more of a sandbox and forget about some of the math. The downsides of simulation methods is they rely on software packages that may have added in features that are hidden that a programmer has made some decisions about. So I am kind of depending on the programmer for having a good mapping between the thing I draw and the numerical method. So if I was doing it myself in a spreadsheet, I would know everything that was written here. But because I'm drawing a diagram and hitting play, I'm hoping the translation from this diagram to this spreadsheet is the translation that I would have made if I would have been doing it myself. And so I'm trusting that programmer who wrote this high-level language. So I might have to look in to the decisions the programmer made in order to get from here to that one there. So that's kind of the downside here. But this is what we're going to be playing with here, is these simulation methods. And there are 3 different types of simulation methods, and I'm not going to worry. I only list them here because I want you to know that what we are learning about is not the be-all and end-all of simulation. So we are going to be doing system dynamics modeling, which focuses on the sort of average behavior of systems over time. If you need slightly more detail, there's something called discrete event system simulation, which allows for randomness to be added into the model. So our models are not going to have randomness, but discrete event system simulations are similar to our models, but they add randomness in, so you get variation, more variation. And then kind of the most micro scale models you can get are what are called agent-based models. And we have some courses in sustainability where we talk about ABMs, where in this case, you really do build virtual worlds where you have to tell every single agent what they're going to do, and they can be random and they can interact in all sorts of different ways. And there's very little mathematical constraints on their behavior. So this is the closest thing to sort of building a virtual world, is this agent-based modeling. Very high fidelity, but because of that, very slow to simulate relative to our system dynamics models. All right, so wrapping up here, system dynamics modeling, it's a branch of control theory that deals with socioeconomic systems, branch of management science, which deals with controllability. So it's a method of analyzing problems in which time is an important factor, in which the study of how the system can be defended against or made to benefit from the shocks that fall upon it from the outside world. So we won't model everything, but we can take a system without shocks and then shock it and then see how it responds to that shock over time. And that kind of gives us a way to play with that. But we're focusing on the average behavior of systems, not the small scale day-to-day sort of variations. So we are going to study how causal structures lead to dynamical patterns on average. So I'm focusing on average here, kind of the focus here. So that's kind of where we're going from this point on. So I think that's roughly all I've got for you. Are there any questions before I remind you of the assignments and then give you the attendance exercise? All right, so just a couple of reminders here. Remember, if you haven't done it, complete the Unit 0 assignments to unlock the rest of the course. There is an assignment A2, which is all on Canvas. That is you basically, so if we would have had extra time, might be able to start on it here, but it basically shows you some examples and asks you about your mental model, so you can knock it out pretty quickly. Otherwise, there's the reading. So we got chapter 1 coming up on Thursday, so take a look at those reading exercises. So this assignment A2 on mental models is due Sunday. Again, should be able to knock it out pretty quickly. So I'll just end with, if I can get the mouse back, this attendance question. So just to get, so if you go to this URL, it should bring up a Google form. If you, you can do this after class as well. You've got about 24 hours after I post the video. If you go to this, it'll bring up a Google form. You have to log into it with your Google or with your ASU account. So if it says, you don't have access, that probably means it's trying to access it with your normal account. So a good trick to get it to switch to your ASU account, which you only will have to do once, is if you go to drive.google.com, like Google Drive, log in with your ASU account, then visit this after you're logged in with your ASU account on your browser, then it should grab your ASU account and show you the form. That form shows you 10 different lines. Just fill out the answer to this question on the top one and then hit submit. You only submit at the end of class. And the question that I'm going to ask is, what is the question that a generic model answers? So I defined a model as something that answers this question. So put that question, that's the answer, that whatever that question the models answer, as the first answer in the attendance here, and just hit submit at the bottom of the page. If you're having trouble with the access, again, I can work with you after class, but a trick is usually you go to Google Drive in your browser, log in with your ASU account, go to this, and then from that point on, every time you go to this, it should be able to do it. If that doesn't work for you, you can also write down that answer on a sheet of paper with your ASU right in the top left, and I'll take care of it that way. Just drop it off to me after. So that's all I've got for you. If you got any other questions, feel free to come up. Otherwise, we'll see you Thursday. The question is, what would, and I see the question online, what does the generic definition of a model answer? Like I said, a model is defined as something that answers this question. What is the blank? Yes, question one on the sheet. And I see there was a question online, why wouldn't, and I don't know if you're still around, but the question was, why wouldn't there be a way to view the numerical model generated? And actually there, in the simulation models, I'll show you as we start building it, you actually can see the numerical model that gets generated after you hit play. And so there is a way to unfurl that, but the point is the mapping there may not be. So if you actually look at that numerical model, it may not have unrolled the way you thought it was. And that might be because of some choice the programmer made. So that's kind of, we're giving a lot more authority to the programmer by using simulation models. And if we were to write it ourselves, we'd have more certainty. So I hope that helps answer that question. All right. So in that case, I will stop the recording or attempt to.